Hello and welcome to your first of two All the Stuff You Need to Know lectures. This is basically designed just to be a review of things that are going to come up throughout the semester that it may have been a while since you learned. Don't worry if you don't know everything that I'm talking about by heart. This is more of just like a heads up to make sure that you're familiar with some of these concepts so that when they come up throughout the course, you're not trying to learn this concept plus also all of the algorithms and data science that we're learning. So again, I'll move to my next slide. Everything's fine. You're fine. This is fine. This is just a heads up, a little review of things that you might want to be familiar with as we move through this course. So the first thing I want to talk about is logarithms. And this is probably something you've heard of, but not something you use all the time. But just as a review, a logarithm is essentially the opposite of an exponent. So for instance, if I have, oh, that's way too big. If I have log base 2 of 8, essentially I'm asking, okay, well, if I took my base, which is 2, to some power, we'll call it x, I want it to equal the number 8. And your logarithm tells you what x is in this case. So if we know our logarithms or our exponents, we know that in this case, x equals 3. So we would say log base 2 of 8 equals 3, because 3 is the exponent that when you take 2 to that power, it equals 8. Now, that's just a review. You don't actually have to calculate logarithms by hand in this class. That's what computers are for and calculators, but I want you to kind of get an idea of what the logarithm does. On the right-hand side here, I have a graph of the log base 2 logarithm, and I want you to notice a couple things. First of all of my inputs are positive numbers. This could go on to infinity if I wanted it to, but obviously I only have a finite amount of paper, so it only goes out to 10. But you can see that my inputs to the logarithm function are just positive integers from 0 to 10. But the outputs, which you can see by the blue line here, are all these negative values and these positive values. So one thing I want you to be familiar with is the fact that logarithms take positive values from 0 all the way to infinity if we wanted, and turn them into a range of values that go from negative infinity to positive infinity. And the way it does it is with this function, and we might use different logarithms with different bases, but that operation is something that I do want you to be familiar with. The next thing that I want to talk about is derivatives. And don't worry, I'm not going to make you calculate derivatives by hand in this class. Again, that's what computers are for. But I do want you to be familiar with the idea of what a derivative is, because that's going to come up a lot in this class. A derivative is basically a rate of change. So if you imagine a function that looks like this weird wavy line that I have on my screen, the derivative is going to be negative when the function is going down, so somewhere like here. It's going to be positive in places where the function is moving up, like here. And maybe most importantly, it's going to be 0 at places where the function is flat. So here, I'll put that here, negative, positive. So the reason why 0 is so important when it comes to derivatives is a lot of times in data science, we're trying to minimize or maximize something. And the places when something is minimized or maximized are always when the derivative is 0, or at least very close to 0 in practical circumstances. So knowing what a derivative is going to help you find those. And remember, when a function is moving down, the derivative is negative. When it's moving up, it's positive. And anytime it's flat, whether at a maximum or a minimum, it's going to be 0. Now to the opposite of a derivative, an integral. Basically, an integral is the area under a curve. And again, not going to make you calculate these by hand, but it's important to know what theoretically an integral is doing. So if you think about this weird shaped curve that I have on my screen, you could use an integral to find the area that's dark shaded green between these two lines under this curve. So if this curve is defined as a function f of x, we can use the integral from x1 to x2 to find the area under the curve between those 2 points. The way that this comes up mostly in data science is when we're doing things with probabilities. So if we have a probability, we can calculate that probability by finding the area under this part of the curve compared to the area under the entire curve. Next, I want to talk about matrices and vectors. And again, don't worry, not going to make you do a ton of matrix algebra by hand. Again, that's what computers are for. But I want you to be able to think of data in terms of matrices and vectors, because a lot of the things that we're working with are going to refer to them as such, and I think it's just a little bit easier. So if you think of a data frame like a spreadsheet, like in Excel or Google Sheets, you can think of that as a matrix, basically. It's a bunch of rows and columns with values in those rows and columns. That's a matrix. We can also call it a data frame. We can also call it a spreadsheet. All of these things refer to the same thing, at least in our context, but it's important to know when you're thinking of data as a matrix. Second, vectors are basically one row or one column. So a vector of all of the ages of people in our class, that would be a vector. It could be one vector in our matrix of data about our classmates, or we could think of a vector as a row, and a row could be just like one person where it has their age and their GPA and their college and etc. Okay, hopefully that made sense. Matrices and vectors are just kind of new terms to think about of things that we already understand. Okay, the next thing I want to talk about is variance and covariance, but I'll start with variance. So the formula for variance is up in this corner here, but I don't need you to memorize that because pretty much anytime you're going to need it, you'll have the ability to look it up. But variance is essentially how spread out our values when we're looking at a single variable. If you think of the two images on the screen as like a number line, you can ask yourself which of these has higher variance. Well, if I were in person in class, I would make you raise your hands and vote, but since we're not, just think of the answer. And now I'm going to tell you that the answer is the second one. This one has higher variance. And that's because it's more spread out. You can see in the top one that all of the data points are very close together, and on the bottom they're all very spread apart. So the second one on the bottom has the higher variance. Now on to covariance. Again, I have the formula for how to calculate this up in the top right corner, but you don't really need to memorize that as long as you understand what covariance is measuring. So if variance is how spread out things are in one variable, covariance is how two variables move together. So if you have two variables, let's say height and weight, and as one goes up, the other one tends to go up, that's going to have very high positive covariance because as one thing goes up, the other one also goes up. If we have two things that are negatively related, like the number of years you've been driving and the amount you pay on your car insurance, hopefully, you can say that that has very negative covariance because as one of those things goes up, your age, the other thing goes down, your hopefully amount you pay for car insurance. If we have two things that have absolutely no relationship to each other, then we're going to have very low but like zero covariance, and that's because there's no relationship between the two things. As one goes up, the other one just kind of stays the same, and it doesn't matter because there's no relationship between them. So if you look at these two graphs on the screen, I can ask you which has higher covariance. Again, I would ask you if we were in class, but just think of the answer. And now I will tell you the answer is the one on the left. And that's because there is actually a positive relationship here, right? Whatever these two variables are, as one goes up, the other one tends to go up. On the right-hand side, you can see it's just kind of an amorphous blob of data points. There's no relationship, so this probably has like zero or close to zero covariance. So the higher covariance in this case is the one on the left. All right, let's talk about the normal distribution. Now, you've probably seen a normal distribution before. You might have heard it referred to as a bell curve. So if you've taken any standardized test or anything, you've probably seen a normal distribution. Now, I'm not going to go into huge depth here, but the normal distribution comes up a lot in data science, so I want you to be familiar with it. And basically, the normal distribution is a very special distribution where it is symmetric. So if I draw a line down the center of it and fold it in half, it would be exactly the same. And it's unimodal, which means most of the data is in the middle. You can see kind of like maybe here of the distribution. Basically, this represents a lot of things in life. You can think of something like height as being normally distributed because most people are like 5, 4, 5, 6, but then we have some very short people on one end and some very tall people on the other, but not very many compared to how many people are in the center. And that's what's really special about the normal distribution, and it comes up a lot, so just keep it in mind. The next concept that I want to talk about is random variables. And random variables basically refers to a variable where there's something that you know about how that variable is distributed or how it's generated, but you can't predict every individual value of that variable. For instance, a really great example is a coin flip. I know something about fair coins. I know that I believe there's about a 50% chance that I'm going to get a heads and a 50% chance that I'm going to get a tails. But if I flip a coin, I can't perfectly predict what it's going to be. There is some random process that's generating the actual data, even though I know something about it. Similarly, we can think of height as a random variable, because if I randomly selected, let's say, a student from Chapman, I know something about the heights of all students from Chapman. I know that it's probably on average 5'6", and again, there's a tail of really short people and a tail of really tall people. But if I randomly select a student, I couldn't tell you exactly how tall they are. Again, it's a random variable. So I want to talk about data types because we're going to do a lot of data analysis, so it's probably important to talk about the different types of data that we can have. I'm actually going to start with categorical data because it's something that we come across a lot. Categorical data, as it might sound, is data where there's only a few categories that your data variable can take on. For instance, I could ask you if you're a freshman, sophomore, junior, senior, and you have to be one of those. It's not like you can have an in-between value. You're one of those 4 categories. Contrast that with a continuous variable. A continuous variable is a variable that can take on infinitely many different values. For instance, if I weighed the exact grams of water that you all have in your water bottles, that's continuous because you could have 6.27 grams or 452.7 grams. There's an infinitely many values of grams of water that you could have. Therefore, it's continuous. Going back to categorical variables, there's a couple different types of categorical variables, and I want to go over them very quickly. The first one is nominal. Say I gave you all a survey and asked you whether your favorite color was red, green, or blue. I didn't give you any other options, so you only had those 3. So we're looking at a categorical variable. There's only 3 options that you could have. And there's no relationship between those 3 colors. Like, it's not like red is higher than blue, which is lower than green or something like that. There's no meaningful order that I could put those categories in. When that's the case, the variable is nominal. There's no relationship, no hierarchy between the categories that we have. When we do have some type of order, then we call it an ordinal variable. One example could be the level of education that someone has. For instance, I could have categories like no formal education, high school or GED, a college degree, a master's degree, and a PhD. So again, discrete categories, I'm only giving you those 5 options, but there is some meaningful order I could put them in. I could put them from least amount of years to most amount of years of education, and that would be a meaningful order I could put it in, from no formal education to a PhD. But what makes an ordinal variable different from an interval variable is whether the difference between each of the categories and the next category is equal. So for example, in the schooling example, is the difference between no formal education and a high school/GED the same as the difference between a master's and a PhD? Well, I don't think so. I think that we could argue that those aren't the same, and so this is an ordinal variable, but not an interval variable. An interval variable, on the other hand, could be like whether you're a freshman, sophomore, junior, or senior. One, there's an order, so it's definitely ordinal. But you could also argue that the difference between being a freshman and a sophomore and a junior and a senior is the same. Every time we move up one category, it's one more year of education that you've had. Now, in real life, it's going to be hard to decide whether things are ordinal or interval. It's usually pretty obvious when there's an order that you can put things in, but we'll often have arguments about whether it's interval or not, whether the difference between each subsequent category is the same. And practically, that's something that you're going to have to deal with as a data scientist, is trying to decide these things. but practically that's what the difference is. Ordinal has an order but isn't the same between each category, and an interval variable is an order and has the same spacing or difference between each of your categories. The next type I want to talk about is a Boolean type, and this is actually similar to categorical, but it comes up a lot because a lot of times we'll have a category like identifies as female, or owns a dog, or is registered to vote, and the data that we have will be a true or false value, so similar to categorical, but just explicitly a Boolean true or false value. The last type of data that I want to talk about, although this isn't exhaustive, there's tons of other types of data that you can have, is text. And I wish that we did more on text here, but we only have so many weeks in the semester. Text data is different from categorical variables because it's not like telling you which category something is in. Text data is more freeform. Like, think about short response questions or addresses or even names. Something where there's not explicit categories, but you're still getting your data in the form of text. Again, it's super interesting, super prevalent, and super useful, but not something we'll cover a ton here, but it's worthwhile knowing that it exists and that we'll usually see it in some of our data sets. Back to the math, let's talk a little bit about probability. So probability is basically the chance that something is going to happen given a set of circumstances. So for instance, I can say like, okay, well, like I live in California, what is the probability that it's going to rain? Well, very low because it's California. The probability is essentially all of the times when something happens divided by all of the possible events or times that we're looking at. So if I wanted to figure out the probability of it raining, I would say what is the times that it rained divided by all of the times whether it rained or not. Sometimes we can think about this in discrete events like did it rain or not, and sometimes we'll think about this in continuous events. So for instance, if you look at the left-hand side of the screen, you can see, let's see, this is a variable that can take on a bunch of different values. We might want to calculate, given that this is all of the values that we can, take on, what is the probability that our value is between 1 and 2? And again, this kind of goes back to the integral part that I was talking about. If we want to figure out what is the probability that our value is between 1 and 2, well, we can take the integral, find the area of this area, and then take it and divide it by the total area of every value that we could have. But sometimes probability is a little easier to think about in the discrete sense when we just have events like rain or not rain. In the case of the right-hand figure, you can see that we have this circle that represents rain when it's this dark blue color, not rain when it's this light blue color. And then in this weird kind of like semi-transparent part, this represents times when we brought an umbrella. So for example, if I wanted to say which part of the circle represents times when it rained and I didn't bring an umbrella, well, it would be this section right here because it's an overlap between rain and times when I didn't bring an umbrella. So when you think about probability, you're basically saying, okay, what is the times when this happened divided by all the possible times? In this case, the circle, the entire circle is all possible events that could happen. So if I wanted to say what is the probability of it raining, I could say, well, it's the area of this section when it's raining divided by the entire circle. So maybe here the probability of it raining is about 20%. Relatedly, I want to talk about conditional probability. Conditional probability is basically like regular probability, but with more information. So for instance, look at the circle. I could say, what is the probability that I bring an umbrella to school, say? Well, that would be this little part of the circle divided by the entire circle. Now, what if I said, what is the probability that I bring an umbrella given that it's raining? Well, that basically tells me, let's ignore every single event where it's not raining. So now if I say, what is the probability of me bringing an umbrella given that it's raining? Well, that's this entire section. And that's pretty high, right? The probability of me bringing an umbrella given that it's raining is very high. This is contrasting with the probability of bringing an umbrella in general when we're looking at the entire circle, which is actually relatively low, which makes sense given that it doesn't rain a lot here. So again, conditional probability is a probability given some other information or assuming some other information. So you could say, what is the probability that I'm a dog lover given that you've seen me pet a bunch of dogs, compared to just what is the probability that I'm a dog lover. Okay, I promise we're almost done, but next I want to talk about odds. And if you've ever been to like a horse race or you've bet on any games or anything, you've probably heard of odds. And odds are just another way to talk about the probability of something happening, but in slightly different terms. So say we have a soccer player and he has a probability of 60% of scoring a goal in any given game. If I wanted to calculate the odds of him scoring a goal, what I would do is I would calculate P divided by 1 minus P. Essentially, this is the probability of that event happening divided by the probability of the event not happening. So if his probability is 0.60, or in other words 60%, then the odds would be 0.60 divided by 0.40. And if I did all the math, you can pull out your calculator if you want, I'll get that the answer is 1.5, which means the odds of this person scoring a goal is 1.5, which means it's 1.5 times more likely that this person will score a goal than not. Let's look at another example. So say that I am flipping a coin and I think it's a fair coin. That means the probability of getting tails is equal to 50% or 0.5. Well then, what is the odds of getting tails? Well, it's the probability of the event divided by 1 minus the probability of an event, which is 0.5 divided by 0.5, which hopefully you don't need a calculator for that, is 1. When the odds of something are 1, it means it's just as likely that something will happen as it won't happen. When the odds are bigger than 1, it means it's more likely that the event will happen than not. And when they're less than 1, it's more likely that it won't happen than it will. Again, odds are just a different way to talk about probabilities of something by comparing the probability of something happening to the probability that it won't happen. Okay, next I want to talk about likelihood, and I'm only going to brush the surface here because it's kind of a complicated topic. But let's think of it this way. Say that the two distributions, the light gray and the black one here, let's say that we want to know which distribution is more likely to have generated a 1. Well, if I look at the probability of getting a 1 under the black distribution, we can see that the likelihood is pretty high, but it's not as high as the likelihood under the gray distribution. Likelihoods are basically a way to consider how likely it is that certain distributions or certain sets of events generated a certain value. Again, here basically we're asking the question, if I observed a 1, how likely is it that I got a 1 in one circumstance, the black distribution, compared to the other one, the gray distribution? In this case, we would say that 1 is more likely under the gray distribution than under the black. We'll step back from the math for 1 second to talk about something a little more theoretical, which is the difference between inference and prediction. And this is something that is a little bit nuanced and weird and something that you might not hear a lot, but is incredibly important to data science because they're very different even though at first they might sound the same. A lot of what we'll be doing in this class is prediction. And essentially, just like it sounds, in a prediction model, what you care about is that the thing that is coming out of your model, your prediction, is accurate. For instance, if I wanted to predict someone's credit score or whether or not they're a Hufflepuff, all I care about in terms of prediction is whether my model is accurate. Does it tell me correctly when someone's a Hufflepuff? Does it very closely guess their credit score? All that I care is what is coming out of the model. I don't really care what went into it or how the model is working, as long as I'm getting the right answer most of the time. Contrast that with inference. Inference is a little different, although it might sound similar at first. In inference, we don't just care about the output, we actually care that the content of the model is accurate to what happens in real life. For instance, if we model a relationship between your favorite color and being a Hufflepuff, in a prediction model, we don't actually care if that relationship really exists in the world as long as it helps us predict whether someone's a Hufflepuff or not. But in an inference model, we do care. We want those relationships to be as accurate to the real world as possible. And this is contrasting with a prediction model where all we care is that it spits out the right answer. Let me give you a really funny story that kind of illustrates the difference here. There was a group at UCI that built a kind of machine learning vision algorithm that was looking to figure out the difference between a dog and a wolf. And they trained it on a ton of images, and it did really well. It was very accurate at predicting when something was a wolf versus when something was a dog. So in terms of prediction, the model did really great. Every time it was a dog, it usually said it was a dog, and usually when it was a wolf, it said it was a wolf. But when they looked closer at the algorithm, they realized that the algorithm was actually looking at the snow in the picture and whether or not there was snow. It figured out that if there was snow in the picture, it was probably a wolf, and if there was no snow, it was probably a dog, which makes sense given all of the pictures of dogs versus wolves on the internet. It's much more likely to see a wolf in snow than a regular dog. So in terms of prediction, again, it was doing a really good job. It accurately told them whether or not something was a wolf. But in terms of inference, this was not a great model because the true relationship between what is a dog and what is a wolf doesn't rely on snow. And so it was looking at a relationship that doesn't actually exist in the real world. So in terms of inference, this model did really badly. Hopefully that helps you tell the difference. Inference makes sure that you're accurately representing relationships between variables that are true in the real world. Prediction just cares whether the answer that your algorithm spits out is accurate. Mostly we'll be doing prediction, but it's really important to distinguish between the two because the way that you go about doing things will maybe be different depending on which one of these things is your goal. You finally made it through. In the next lesson, we'll talk a little bit more about Python. We'll download a bunch of packages that we're going to be using and make sure all of that is working. I will see you next time.